Welcome to the Inamena CSP video tutorial. This is Block 2, Unit 2 about the measurement of solar radiation. My name is Stefan Wilbernd. In this unit I will speak about ground measurements and also about satellite-based assessments. We can measure radiation with thermal sensors. In this picture we see a solar tracker. The tracker follows the sun using an algorithm. The input for the algorithm is the time, the longitude, the latitude, the height and the pressure for the special site. The Ni is measured with a pyrheliometer. GHI is measured with a pyranometer. And DHI is measured with a pyranometer that is mounted behind the shadow ball. The tracker in the photo also has a sun sensor. The sun sensor is a 4-quadrant sensor. It controls and corrects the tracking. Thermal sensors use thermopiles as sensors. For example, we see in the photo on the right hand side the black-coated thermopile of a pyranometer. Thermopiles measure radiation by measuring a temperature difference that is caused by this solar radiation. This temperature difference then causes a voltage that we can measure with a data logger. On the left hand side we see a photo of a pyrheliometer. Here the thermopile is positioned at the end of the tube. In the photos we see two different pyrheliometers, one from Kip & Sonen, the CHP1, the other one is from Apley, the NIP. The entrance windows of pyrheliometers are usually made of silicon oxide. This is to allow a good flat spectral response between, let's say, 300 nanometers and 4000 nanometers. The pyrheliometer consists of a tube with additional apertures to stop stray light, and optionally there are temperature measurements close to the thermopile. These measurements allow us to correct temperature effects of the thermopile. Pyrheliometers can reach an uncertainty between 1 and 2%, and this holds for ISO 9060 first-class pyrheliometers. There are two different types of pyranometers, only black and black and white pyranometers. Only black pyranometers have the hot junctions of the thermopile under the black area, and the hot junctions of the thermopile are heading upwards, while the cold junctions of the thermopile are heading downwards. Only black pyranometers can have a single or a double dome. Two domes are an advantage, especially also when used with a ventilation unit, because like that you can avoid the effects of a cold dome on the signal. The same thing happens also with a ground, so you know that there's ground frost sometimes, and like the ground, also the glass dome can cool down. The cold glass dome can then reduce the signal of the thermopile artificially. Black and white sensors have the hot junctions under the black part of the surface of the sensor disk, and the cold junctions are under the white part. Black and white sensors can work with a single dome without problems. The reached uncertainty of pyranometers is between 2 and 4% for GHI. If we want to measure DHI, we need a shading structure. There are different shading types. I already showed you the shadow ball. There are also shading disks. So instead of the shadow ball, you can also mount a shading disk perpendicularly to the solar vector. You can also use a shading ring. This is simple and cheap because you don't need a tracker. You have to adjust this shading ring after some days, and well, because the sky is partially covered and you do not only cover the sun, some correction functions are necessary. In the end, your DHI measurement with a shading ring is not very accurate, and we have to say that it's not accurate enough for CSP. Now I want to come to the calibration of irradiance sensors. For thermal sensors, you need a factor between the output voltage of the thermopile and the irradiance. Pyranometer and pyrheliometer calibration scales are traced back to the World Radiometric Reference, WRR. This WRR is represented by the World Standard Group, WSG. This group is a group of absolute cavity pyrheliometers. I will show you this instrument type on the next slide. On this slide you can see a photo for one example. The WRR WSG is maintained by the World Radiation Center in Davos. Absolute cavity radiometers have to be tracked to the sun, so they are pyrheliometers. They have an open phase. In this open phase, light heats up an absorber so that a temperature difference is created by the light. Then we have a closed phase. In this closed phase, the aperture of the pyrheliometer is closed and the same temperature as before is created with an electrical power. It's easy to measure the electrical power, and if you then also know the size of the absorber, you can obtain the DNI. Characteristics of absolute cavity radiometers are the following. They are called self-calibrating because of the two phases. The uncertainty is quite low. It reaches approximately 0.3%. They are usually not weatherproof because they don't have entrance windows, and, well, they are quite expensive. They will cost you like 10 times the price of a field pyrheliometer. Also, you will only get chopped measurements from absolute cavity radiometers. The calibration of pyrheliometers and pyranometers is necessary, as I said, and it works like that. For field pyrheliometers, you can perform a calibration with the WRR or with reference pyrheliometers. In the latter case, the reference pyrheliometers are calibrated with the WRR. Reference pyranometers can be calibrated using reference pyrheliometers and movable shading structures above the pyranometer. Pyranometers can also be calibrated using reference pyranometers. The reference pyranometers have to be calibrated with the pyrheliometers, as I mentioned. In the photo, we see an example for a calibration that was performed here in Tabernas. There are also photoelectric sensors, so instead of a thermopile, the sensor element can also be, for example, a photodiode. The spectral response of photoelectric sensors is not flat and it does not match the solar spectrum. This can be seen in the graph. On the left y-axis we see the spectral irradiance in watts per square meter and nanometer. On the right y-axis we see the relative Likert response. So the Likert pyranometer is one example for a photoelectric sensor that is shown here. The x-axis shows the wavelengths of the light in nanometers. We see three curves. The green curve for the global irradiation following ASTMG 173. We see in red the direct irradiation, and in blue the Likert sensitivity is shown. As you see, in the blue part of the visible light, the Likert has a very low response. In the end, this leads to higher uncertainties for photoelectric sensors than for thermal sensors. Now I want to sum up some radiometer characteristics. First of all, the calibration stability. We have to ask ourselves, can the radiometer maintain a calibration over a long period of time? Then there's something like the cosine response. So are the optics of the instrument of a high quality so that the signal output is independent of solar elevation? Temperature stability. Will a given input provide the same output voltage independent of temperature? The spectral quality. Is the instrument spectrally flat across the solar spectrum so that it responds correctly to changes in the solar spectrum? And then the tilt. Does the instrument behave the same when tilted? For pyrheliometers, this is very relevant because they have to be tilted during the day, and the convection of air in the pyrheliometer tube might cause a different response for different tilt angles. Now some words about the reference GHI. Reference GHI is calculated from DNI and DHI if DNI and DHI measurements are available. Why do we do this? Pyrheliometers are more accurate than pyranometers. Also, we have to consider that a slightly wrong leveling of pyranometers affects the GHI measurement more than the DHI measurements. And then we have to consider also that DHI is small. So in the end, this means that the uncertainty of the calculated GHI is lower than the uncertainty of a directly measured GHI. Now I want to say a few words about quality control of data acquisition. So if your sensors are in the field, you have to check if the sensors are clean. Make sure that they are cleaned daily. You have to check the leveling of the pyranometers. Usually pyranometers come with a water level. You also have to check the leveling of the tracker. And you have to check the position of the shadow ball. The tracking of the pyrheliometers can be checked with the light spot. So here pyrheliometers have a hole in a metal plate, and here there's a metal plate with a mark, and on this metal plate you can also see the light spot connected to this hole. In this photo we see that the light spot is on the mark, so the tracking is okay. In this photo the light spot is close to the mark but not on the mark, and this is not acceptable. Even after the data acquisition, you have to do a quality control of your data. You have to ask yourself, are the values physically possible? There are some physical limits of the variables that can help. Then you can ask, are my measurements reasonable? You can compare your measurements to a clear sky model, for example. And then you can ask yourselves, are my measurements consistent? For example, you can compare redundant information. If you have measured GHI directly, and if you measure DHI and DNI, you can compare calculated GHI and measured GHI. After that, you also have to do a visual inspection of the data. So you should daily look at the graphs of DNI, GHI and DHI and check if there are some unrealistic values. For example, here we see a cleaning event, and of course this data point has to be corrected. Sometimes it's very helpful to have all sky images like this one. So an all sky image can show you if the tracker was tracked, if the sensors were wet, for example, and like this you can interpret your data much better. So to sum up, precise thermal sensors are mounted on a solar 2-axis tracker. The advantage is that they have a high accuracy between 1 and 2% for DNI. You have separate sensors for GHI, DNI and DHI, and this allows you the cross-check through redundancy. The disadvantages of thermal sensors are the high costs, not only for the sensors but also for operation and maintenance. Soiling is an issue, especially for pyrheliometers, and you have to provide a high power supply. Because of these disadvantages, rotating shadowband irradiometers are important. The abbreviation used is RSI. RSIs measure DNI, GHI and DHI, so they are an alternative to trackers plus thermal sensors. Rotating shadowband irradiometers can be seen in the pictures here. So you have a pyranometer. In this photo here, the pyranometer measures GHI. The shadow band can be seen here and also here. This band rotates approximately every minute. During the rotation, the signal is locked with a high frequency, and when the shadow falls on the sensor, more or less the DHI is measured. There are also other names for RSIs: RSP, rotating shadowband pyranometer, and RSR, rotating shadowband radiometer. In this slide I want to show you the principle of operation. So here we see the RSI during the rotation of the shadowband. In the graph we see the intensity measured with the pyranometer in watts per square meter, plotted versus the number of the measurement during the rotation. The rotation needs approximately 1.5 seconds for this RSI, and during the rotation the signal is locked with a high frequency, as I said. So let's look at the curve. Here the shadow band has no effect on the measurement, so this is the GHI. Then the shadow falls on the pyranometer, and then we can measure the DHI. As you see, the DHI is not the minimum of the curve. It's slightly higher than the minimum. We have to correct for the blocked sky radiation. The shadow band does not only block light coming from the sun, but also light that comes from the sky. This correction is done using the shoulders of the curve. So we see that there's a difference between the shoulders here and the GHI. So we add this difference to the minimum of the curve to obtain the DHI. If we then have DHI, GHI and the solar elevation angle, we can calculate DNI. Because you need to lock the signal with a high frequency, you cannot use thermopiles for this type of RSI with a continuous rotation. Thermopiles usually have a response time of approximately 5 seconds, so they are too slow. There are also RSIs with a discontinuous rotation radiation. In this case, the shadow band moves until a region close to the solar disk. It stops. Then you measure the shoulder values. Then the shadow band moves so that it covers the sun, and you measure what we saw here as the minimum of the curve. Then the rotation continues. RSIs have a big advantage if we compare them to pyrheliometers. That is the effect of soiling on the sensor. This is explained in this sketch here. So we have direct solar radiation falling on an RSP and on a pyrheliometer. We can see some dirt on both sensors, and in the case of the pyrheliometer, this dirt leads to a significant signal reduction because the light is scattered and the rays that are scattered do not reach the sensor that can be found here at the end of the pyrheliometer tube. In the case of the RSP sensor or the RSI sensor, the scattering of the rays does not reduce the signal significantly because the rays hit the sensor anyway. This advantage of RSIs was also shown experimentally. In the graph, we see the relative error of daily DNI sum between the calculated DNI of cleaned pyranometers and the measured DNI of uncleaned pyrheliometers and an uncleaned RSI. So again, the reference is the DNI that was calculated from cleaned pyranometers that measure GHI and DHI, and we compare the data of an uncleaned pyrheliometer and of an uncleaned RSI to this reference. For the RSI, we see the results in green. So in the first 2 weeks, we see some negative and some positive deviations. At the end of the comparison, we can see that the RSI is dirty, and therefore we only find negative deviations. For the pyrheliometer, the situation is different. Here, the relative error increases practically day by day. RSIs also have disadvantages. That's why I want to talk about the uncertainty and systematic errors of RSIs. The systematic influences that have to be mentioned here are the sensor temperature, the dependence of the signal on the incidence angle, and spectral effects. The Leica sensor, the Leica pyranometer, is a photodiode which has a low sensitivity for blue light. And exactly this sensor is usually used in RSIs. In the graph, we see again the spectral irradiance in watts per square meter and nanometer on the left y-axis, the wavelengths in nanometer on the x-axis, and on the right-hand side we see the relative Leica response. We see the green curve for the global irradiation, the red curve for the direct irradiation, and the blue curve for the Leica sensitivity. So this has to be corrected with special correction functions. The correction functions also correct the effect of the incidence angle and sensor temperature. Here we see a graph that shows us the effect of the incidence angle from a paper from Augustin. There are different correction functions, for example those by King, Vignola or Goyder. After the correction, the uncertainty is more or less 4% or a little bit lower. This is a value that has been derived empirically, and it holds for 10-minute averages of DNI. RSIs have to be calibrated too. One option is to do so with parallel measurements of RSIs and thermal sensors under real sky conditions, as we see in the photo. After the correction, the accuracy of the RSIs was more or less 4%, as I said. For pyrheliometers, just to remind you, it is 1 to 2%. So to sum up, the RSI has an advantage because it's quite cheap, the maintenance costs are low, and soiling is not so important. Also, the power supply is low, so it's easy to supply the power using a PV panel and a battery. The disadvantages are that you need special corrections, and even after the corrections, the RSI is less accurate than a precise pyrheliometer. Besides irradiance, other meteorological measurements are necessary. For example, wind speed and wind direction have to be measured, air temperature and relative humidity, have to be measured too. Also, the ambient air pressure plays a role for CSP. And there are, let's call them, advanced parameters that are relevant for CSP. For example, the sun shape. So this is the radiance profile of the sun and the circumsolar region. Then the soiling of plant components is important, and also precipitation. And for tower plants, the attenuation or the extinction of radiation between the heliostat and the receiver is of importance. And there are more examples for advanced parameters that have to be measured for CSP. Let me say a few words about the availability of ground-measured data. There are long-term measurements from meteor stations that can be provided by national meteor offices, by research institutes, or such measurements can come from measurement networks. For example, the World Radiometric Network by WMO or the Baseline Surface Radiation Network, BSRN. In the end, we have to say that DNA data is rare. GHI is measured at more sites, and therefore there are statistical global-to-beam models that allow you to derive DNI based on GHI. However, the models can only give you rough derivations. Because there are so few stations, the spatial resolution that you can obtain from ground data is low. Therefore, spatial interpolation techniques were created in order to derive maps and site-specific data. So to sum up, ground measurements can reach high accuracy, let's say between 1 and 4%, and they can give you a high temporal resolution. 1 minute is no problem. The disadvantages of ground measurements are that the database is small, so usually you only have a few years of data and you only have few sites close to the interesting site where you want to put your CSP plant. 7 to 10 years of measurements are necessary to get a long-term mean within 5%. And, well, if you then have only a few years, this is not enough. Also, you have to have data from 2 kilometers or less away from the planned CSP site. So this means that the small number of available sites of ground measurements is also a problem. And, well, the high costs for the sensors and also for operation and maintenance is a disadvantage. Because of these disadvantages, I want to talk also about satellite-based radiation measurements. I'll start with the principle of operation. So, if we look at the calculation of solar radiation from remote sensing, we will start with the extraterrestrial DNI. We want to get to the DNI at the surface. The first step is an atmospheric model that allows us to calculate the clear sky DNI and the clear sky DHI. So this means that we then also have the clear sky GHI. So, let's first talk about the atmospheric model. In this slide we can see how the radiation falls on the atmosphere and how it is absorbed and scattered and reflected before it comes to the ground. So ozone absorbs parts of the light, air molecules cause Rayleigh scattering and absorption, aerosols cause scattering and absorption, clouds can reflect, scatter and absorb the radiation, and also water vapor plays a role because of the absorption. For the clear sky model we need some input concerning ozone, the air molecules, aerosols and water vapor. Here are some examples for the input for clear sky models. If we want to calculate a whole map in the end of DNI, we can use GACP or match for the aerosol optical thickness. This is the most important parameter for aerosols. We can use NCAR or NCEP for water vapor, and information from the TOM sensor can be used to get information on the ozone. So we now followed the way from the extraterrestrial DNI to the clear sky GHI and the clear sky DNI. Now we have to include information on clouds, and this information can be obtained from satellite images. This is explained in the 3 pictures on the right hand side. So let's say we want to calculate the DNI on the ground for the time at which we took this picture. We can compare this picture with an image of the same area without clouds, and by this comparison we can obtain cloud information. So then it's possible to calculate the surface GHI. Another step is necessary then. This step is the step from the surface GHI to the DNI on the surface. In order to determine DNI from GHI, diffuse fraction models are used. These models split the global radiation in the components diffuse and direct. They are mainly related with the clearness index KT. This clearness index relates the global radiation incident on the Earth's surface to the extraterrestrial radiation. The input for the splitting is also the solar elevation, the turbidity, the hour-to-hour variability, and the surface albedo. The splitting process depends heavily on empirical tuning and is therefore not very accurate. Satellite-based solar assessment gives you different results. For example, you can obtain information for single sites like time series, sums, and so on. It allows you to long-term analysis. You can obtain up to 20 years of data. You can create digital maps. For example, here we see the annual sum of DNI in 2002 in the Mediterranean region. For example, the temporal resolution of the input data can be 1 hour, and the spatial resolution of the digital map can be 1 kilometer times 1 kilometer per pixel. So maybe you can ask now, why do we need ground measurements? First of all, the accuracy of satellite data is only between 10 and 15%, while the accuracy of ground measurements for DNI is between 1 and 4%. Also, the time resolution of satellite data is quite low, so sometimes you have 15-minute resolution, sometimes 1 hour, while the ground measurements can be obtained with a resolution of 1 minute without problems. Since DNI has an overproportional influence on the costs per kilowatt hour of a CSP plant, we have to say that 10 to 15% accuracy is not sufficient, and therefore ground measurements are not obsolete. Instead, ground measurements have to be combined with satellite data. In this slide, I want to compare ground measurements with satellite-derived data. Ground measurements have quite high accuracy, depending on the sensors, and they obtain a quite high time resolution. The disadvantages of ground measurements are the high costs for installation and also for operation and maintenance. Soiling of the sensors is an issue. Sometimes you have sensor failure, and of course, it is not possible to gain data of the past. Satellite-derived data has different advantages. For example, the spatial resolution and the availability. Also, long-term data is available. Effectively, there are no failures, and soiling is not an issue for satellite-derived data. In the end, the costs are low for you because the satellites are paid by somebody else. The disadvantages are the time resolution, which is too low for CSP, and the accuracy is not sufficient. So, what I want to say is that we don't have to understand ground measurements and satellite-derived data as competing parties. Instead, we have to see that the combination of both data sources is the important thing. So I want to come to the end of this Block 2, Unit 2, concerning the measurement of solar radiation. We talked about ground measurements and satellite-based assessments. I would like to thank Robert Pitzpal and Carsten Heuer-Klick for previous versions of this presentation. I also want to thank Norbert Geuder and Christoph Schillings for a large number of slides. And I want to thank Fabian Wolfertstetter for reviewing the slides. Thank you for your attention.